Okay, all right. Okay, so this will be a metal, right? So why this will be metal? Because I can take one electron from the field Fermi C, and I can give it infinitesimally small energy to pull it out of the Fermi C and set somewhere here, okay, above the Fermi C. Okay, so that's why with infinitesimal small energy I can actually excite particles. Okay, so that's why these things are called electron, or these things are called metal. And yeah, so these are the main ideas when you talk about insulator or metals, right? So when you say that whether a system is a topological insulator, that means that if we look at the bulk band structure, so then we are expecting a gap. But on the other hand, if we look at the edge of this system, then we'll see a gapless thing like this. Okay, so this is what a topological insulator is. Okay, so and it turns out that if you have the information about the bulk, okay, then you already know what you are expecting at the edges. Okay, so this is a very important principle, so which is called a bulk boundary correspondence. Okay, so let's say from the bulk you can calculate some quantity. Okay, you can calculate some quantity, let's call it C. Okay, now if the C is non-zero, then it will automatically tell you have some edge states. Okay, if C is non-zero, that means you will have some edge states. Okay, and if C is 0, then no edge states. So this is the broad idea of bulk boundary correspondence. So you will always be able to calculate some quantity like this. Okay, so this is called a topological invariant. So I'll define it in a more precise way soon. So this is called a topological invariant, and topological invariant in the bulk, in the or let's say in the momentum space, will guarantee that there will be edge states on the edges of the sample. Okay, so these are the main idea of what a topological insulator is. So normally so let's talk a little bit about phase transitions. Okay, so topological, or let's say, so we can actually drive a phase transition in these topological insulators by changing certain parameters of the Hamiltonian. Okay, so what do we mean by phase transition? So let me remind you what the main idea of phase transition is. So normally all of the things that you have learned as of now is basically belongs to Landau phase transition. So what happens that, so in this kind of paradigm, so each of the phase transition is indicated by a broken symmetry. Okay, so the phase transition indicates that we are going from a disordered phase to a ordered phase. Okay, so I'll give an example of what a disordered state is. So a disordered state is something like a let's say paramagnet. So what happens in paramagnet is that we have some spins, and spins are not aligned at all, so they are aligned in a random direction, right? So there is no magnetic order. But I also know about ferromagnetic phases, right? So in ferromagnet, what happens is all of the spins are aligned. So this means that I am actually going from a disordered phase when all of the spins were misaligned to a phase where all of the spins are aligned. Okay, so basically all of the phase transitions that you have seen it belongs to this kind of paradigm. Okay, in some way you are breaking some symmetries. So for example, so if you know group theory, so the paramagnet, this orders, I mean this Hamiltonian actually and state obeys the O3 symmetry. So O3 is the rotational group in 3 dimension, right? So that is called the O3 symmetry. And the ferromagnet, it actually obeys a O2 symmetry. So why this is a, so for example, so in this kind of a state, okay, if you change any of the spin, I mean all of the spin by same rotation, okay, then you will see that that is still the same paramagnet. Okay, so your underlying state doesn't change if you do some operation from this O3 group, orthogonal 3 group. On the other hand, if you have a ferromagnet, so ferromagnet always chooses a particular direction, let's say z direction. So then that means that your one particular direction is fixed. Then any rotation that you can possibly do that will keep this state to be non-invariant, that is just this kind of a 2D rotation. So like if you have a spin, so you can just do a 2D rotation. So you can spin, you can just rotate the, I mean in a screw-like fashion. You cannot change the z direction because that is already predefined in a ferromagnet, but you can actually do this 2D rotation. So 2D rotation in so 2D rotation belongs to this O2 group. So that means in a group theory language, we are going from a higher symmetry to a lower symmetry when we are when we are making a phase transition. Okay, and so in this two phases, the aim, so the local moment is actually 0 in paramagnet. Okay, but as soon as you go to ferromagnet, the local moment becomes non-zero. Okay, so these things are called order parameter. So but I'll show you soon that in topological phase transitions there is no notion of order parameter. Okay, so we'll go to that soon. All right, so this is a very well known paradigm of phase transitions. Like most of these phase transitions are basically this Landau phase transition. So liquid to solid phase transition, also Landau phase transition. Okay, so any phase transition you can think about, most likely it is a Landau phase transition. Okay, so on the other hand, these topological insulators, they go through a different kind of phase transition. So let me draw the differences between this. So this topological phase transition is not governed by symmetry. So that means that you will actually change something, some topological invariant in this phase transition, but you will see that the ground state actually doesn't break any symmetry. The ground state will have the same symmetry as it would have for the other phase. Okay, so that is the meaning of it. It is not governed by any symmetry. So it is in stark contrast. It is different from Landau phase transitions. Okay, so and there is no local orders. So there is some, so like I mentioned that there are topological invariants, so some number, okay, right? So which is not a, which is nothing, not that I measure at each of the points, each of the sites of the system. It is like to calculate these numbers, I take account of the full system. Okay, so in that sense, these are not local order parameters like this this moments are, or the magnetization are. So it is not in that sense local, it is a global, because to calculate this topological invariance, I have to take account of the whole system. Okay, it is kind of integrating over the whole system to find out the number. So in that sense, this is not a local order. Okay, so this is actually a global kind of a marker. Okay, and so it turns out that these topological phases are very flexible in the sense that if you add something, some small perturbation to the Hamiltonian, it turns out that this topological invariants like C, they don't change, okay, under small perturbation. Okay, so that means we have actually a lot of flexibility when we talk about topological phase transitions. So we don't have to talk about detail of the model, but here on the other hand, this Landau paradigm actually depends a lot in details. Okay, you have to mention each and every detail of the system, and depending on if you change the details slightly, then the transitions will also change, right? But it turns out that the topological invariance actually doesn't change. So these topological phase transitions are actually not susceptible to this kind of small changes, and this topological invariance will stay the same if you add small perturbations. Okay, so small perturbation means that some perturbation which doesn't let's say cross levels, okay, which doesn't induce level crossing. So that is a example of a small perturbation. Okay, so now so these interesting properties of topological insulators and topological phase transitions, these are actually governed by some symmetries. Okay, so if you know all of the symmetries of the Hamiltonian, then you can actually talk a lot about what is the topological invariant of the system will be. Okay, so topological phases are protected by symmetry. Okay, so mainly we'll be talking about some symmetries. So these three symmetries. So time reversal symmetry, and will be charge conjugation or particle symmetry, and there is a chiral symmetry which is given by, or let me write it as, which is given by time reversal times the conjugation. So these three symmetries actually, these three symmetries actually protect all of these things that topological insulator has. Okay, so it turns out that if you, by adding certain kind of perturbation, if you break symmetries, then you can go to other different topological phases. Okay, so you have to break symmetries also, which is actually a very hard thing to do, energetically speaking. Okay, so so normally when you talk about symmetry, so we have a very clear idea of what does the symmetry mean. So when you talk about symmetry, so symmetry means that the Hamiltonian actually commutes with some symmetry operator. Okay, so this commutator is 0. So that means I have that symmetry, and if I have such a operator, let me write it like this. Yeah, it is 0. So if I can find an operator A which actually commutes with the Hamiltonian, then I can convert the Hamiltonian into the basis of that A operator, and it turns out that actually simplifies a lot of calculation. Okay, so let's say A can be written in terms of it has a eigen decomposition like something like this: U, some lambda, and U dagger. Okay, so now it turns out that if I write H in the basis of A, that means if I write H as something like U, H, U dagger, then the Hamiltonian, this HA, actually attains a block diagonal structure. So it will be just some block diagonal where each block will be identified the eigenvalues of A. So here the eigenvalues of A are, let's say, a good quantum number for U. Okay, so this is the clear notion of symmetry that we learned from quantum mechanics. Okay, so by identifying some operator like this, we actually simplify our calculation a lot, right? Because initially our Hamiltonian would be like a full sparse matrix, so which will be like fully filled, okay, which will have everything all over the place. So then diagonalizing that larger Hamiltonian is considered tough, right? You have to take help of a computer. But on the other hand, as soon as you have decomposed this into this kind of block diagonal forms, so then you can take each of the block one by one and study all of their properties. Okay, then the problem becomes a lot simpler. Okay, so whenever we start to solve some problem, the first thing we'd like to see is there any symmetries in the Hamiltonian or not. So this is what I mean what symmetries do to the Hamiltonian, and this is all of these things are familiar to you. But so when you talk about symmetries, so they actually come in two flavors. So symmetries, so they will be either unitary or they will be anti-unitary. So unitary means that the symmetry that I am talking about has a it can be written in terms of unitary matrix, okay, where this u dagger u is just identity, okay. On the other hand, if I have anti-unitary, then a single unitary operator will not do it. I will have to also add a conjugation, okay. So this k is conjugation, k is equal to minus I, okay. It changes I to minus I. So the symmetries come in these two flavors, this unitary and anti-unitary. So the unitary symmetries are so in a sense they are trivial, because that gives you some good quantum numbers and you can reduce your Hamiltonian to block diagonals. But anti-unitary symmetries, they actually are very non-trivial in that way. So they don't give rise to block diagonal structure, but they give some restriction to your Hamiltonian, okay. So you are most likely familiar with this unitary operator or unitary symmetries. But now, today we will look into some of these anti-unitary symmetries, okay, and how does this give rise to different constraints on the Hamiltonian, and how does that leads to different topological insulators, okay. So that is what we will do. So this all of these things will be hopefully clear by the end of today's session, okay. So let me define symmetry in a let's say theoretical sense. So when you talk about symmetry, and so now so we'll be talking in the second quantization language, so that I mean just bear with me for a while. So the symmetry is defined like this. So I have u, so I have some field operator psi I and u inverse. So if this is some transformation, so this some transformation, it will actually mix these psi's linearly, okay. So it will be given by something like this, u I j and psi j, okay, and there is a sum over j, okay. So that means I am doing some transformation on this field operator, okay. Now what is the action of this u? So that actually linearly mixes all of the field operators, okay. So you can think of this as a rotation, okay. For example, if you have some r vector, so let's say r vector was some 1 0 0, and then if you act some rotation matrix r theta, okay, some rotation matrix on this thing, so what will happen is, so the r theta acting on r will give rise to different things, right? So some a b c, okay. So it will mix all of these three different basis vectors basically. So that is the idea of this symmetry. So these psi's are field operators, okay. And similarly you can write a expression for the dagger also, which is given by just the dagger of the previous relation, okay. So this is 1 and this is 2. So this is how we are defining the action of this symmetry operator u on this field operators, okay. So this is like defining the representation or defining the action. Okay, my screen got stuck. Okay, let me rejoin. All right. Yeah. So this is my okay. So this is the symmetry operation. Okay. And so now I'm imposing that the Hamiltonian is also invariant under this symmetry. Okay. So now just so let me remind you, this all of this H, psi, U, these things are in second quantization. Okay. So this is similar to a commutator. Okay. So any symmetry, whether it be unitary or anti-unitary, in second quantization it will always mean that your Hamiltonian commutes with that particular U, okay, or that symmetry operator. Okay, so this is always true for either unitary or anti-unitary symmetries. Okay, so now now let's say if this is a unitary symmetry, so if this U is unitary, then you can show that. So I'll show you an example of this. You can show that you can go to a matrix representation, so where this Hamiltonian so okay, so let me first write it down. So you can show that if you starting from here, you can show that if you write represent all of these second quantized operators in terms of matrices, then the unitary symmetry will imply this. So this is the relation that we know from our quantum mechanics. Okay, so but here we have started from second quantization and we have shown that this is actually true if I can write the Hamiltonian and symmetry operators in a matrix form. Okay, so the H, second quantized H, is normally given by something like this in second quantization. So now by matrix form I mean that you can write, for example, let's say for two-dimensional Hamiltonian, you can write something like this. So H11, H12, H21, H22, psi1, psi2. Okay, so by the matrix H, so you see that this I'm using different typefaces for this. So I have some cursive H and some normal H. Okay, so when I write the matrix, so that means that I am basically writing this. Okay, and when I write this U matrix, so then that means that I am writing this U matrix. Okay, so if you have any unitary symmetry, you can just do this operation and you can prove this in a very simple way. So I'll show you this for a particular symmetry operator. So let's see this example for a rotation, a physical rotation. So what does the rotation do? So rotation actually changes an x to x prime, which is related to x by rotation times x. Okay, so I'm not being very careful about vectors and matrices, but I mean this is, I mean you can see that if these are vectors, then this has to be a matrix, right? Otherwise this doesn't make sense. So this is a rotation matrix. Okay, and this actually rotates this vector. Okay, if you like. So so let me first define how does this rotation actually this acts on this many body Hilbert space. Okay, so that means, so I have some cursive R. Okay, so which is some rotation operator in second quantization. Okay, so this, when it acts on the field operator which has an argument x, then this thing is given by uij and then psi j rotation times x. Okay, So this is now I have defined the action. So when you do this when you act this R, which is in second quantized language on this field operator, so what it does is it just rotates the coordinate and it doesn't do anything else. So I get linear combination of all such rotated field operators. Okay, so that is the main idea. So this is one. Excuse me. Okay. So this is one of the equation, and I will need a similar equation for psi dagger as well. So for psi dagger, I have already shown you that this will look similar, but instead this will be a dagger, and my u will have similar dagger and j comma I. Okay. So this is the action of rotation operator on this many body Hilbert space or Fock space. Okay, so this is like, you can say this is representation of this rotation operator. So now this is fine. Now I am asking some question, which is like, if my Hamiltonian is also invariant under this rotation, that means if I can write this as H, then what is the restriction on the matrix? Okay, so that is, I mean, that is a straightforward question, and we'll see that how does the answer turns out to be. Okay, so now, so the H, as I mentioned before, is given by some psi I dagger some H ij matrix or psi j. Okay, so and there is summation over I and j. So we can think of this psi ij's as some quantum numbers, or you can also assume that these are some spatial indices, lattice indices, or in something like that. So let me actually write this Hamilton in a block momentum basis. So then the Hamilton would look something like this. So I will have psi dagger I, which is a function of now momentum, block momentum k, and then I will have this matrix element I j and h of k, and then psi j of k. Okay, so now this is something that you already know. So this hk is called the block Hamiltonian. Okay, so now I have to apply these rotations on this Hamiltonian. So then you can see that it will go through this summation, and it will directly hit this these two field operators, which are in the which are in the block basis, right? So but here I know the action of rotation in real space. Okay, so given this action of rotation in real space, I have to first derive what is the action of these rotation operators in momentum space. Okay, so let's try to do that. So for block for this system on a lattice, or a periodical system on a lattice, so this field operators has a mode expansion. So these field operators are given by 1 by square root n summation over k e to the power I k x and psi I k. Okay, so this is like a Fourier transform, or this is like a discrete Fourier transform if you like. So and similarly I can also write for dagger. So you see, when I take the dagger of this thing, so I get a minus on the exponent, and the field operators are just conjugated, like they are just dagger. Okay, so what I will do is, so let's call this equation 1 and equation 2. Okay, so I will apply R and R inverse in equation 1. Okay, so that is that is what I will do now. So that means on the left hand side I will have this R, which is in second quantized, which is a second quantized operator, and then psi I field operator x, and then R inverse. Okay, So this is the left hand side of equation 1, and similarly the right hand side is, so I'll just keep this 1 by square root n here, because the rotation operator will just go through all of the constants, summation, everything. So it will directly go and it will hit the field operator in momentum space. So psi I k, h I j k, and psi j k are inverse, right? So this is both left and right hand side that I have written now. So I have already defined what this quantity is, right? So what this does is, this rotation actually rotates this spatial coordinate, right? So I have already defined this operation like in this equation. Okay, so let's call this, let's see, equation A and equation B. So I'll write that from A, so I'll just substitute the left hand side, so which is given by j u I j and psi j. Okay, so this is the full. Okay, so there is a rotation matrix I'm missing, so rotation matrix X. Now please note that this rotation is just a 3×3, let's say, rotation matrix in 3D. Okay, but this cursive R is a rotation operator in second quantized form. Okay, so which are different. So I'll have so the right hand side I'll just keep as it is for now. Okay, so now for this thing, for psi j, I'll again use a mode expansion given by equation 1. Okay, so equation 1 was this Fourier transform, right, or mode expansion, so which is a mode expansion for psi of x. So now I'll use this for psi of rotated x. Okay, I'll use the same mode expansion. So now when I will do that, so let's do this step by step. So there is j summation, so sum 1 by square root n, and also k summation. Okay, so I will have this u I j right, so psi j k, and in the exponent I'll put e to the power I k dot r times x, right? So this is what how we do the Fourier transformations, and the right hand side I'll again keep the same. Okay, so what I am doing here. Okay, yeah, so let me take a step back, and so the right hand side is wrong. Okay, so this is okay, so let me yeah, so there are some typos, let me fix those. So this is not about h, this is about the field operator. So I wanted to put the mode expansion in here, e to the power I k x and psi I k. Okay, so similar thing here. And similar thing here as well. Okay, so now, so these dot products are actually very nice things to handle. So this k dot r, so k dot r times x, so this is actually, you can check, this is actually same as r inverse acting on k dot x. Okay, so I'll use this identity, I'll replace this this exponent with this r inverse k. and I'll keep the right hand side to be the same. So yeah, so this is fine for now. Okay, so now what I will do is, on the left hand side I'll do this change of variable. So because this is a summation, or you can also think about this is an integration, and I'll just do a change of variable. So I'll change my k to be some rotated k. Okay, so so you'll see why I am doing that. So that will simplify some things. ij psi j. So instead of k, I'll write rotated k, r times k, and the exponent, so the exponent will get simplified, and then I'll have k dot x in the exponent. Okay, so because k is a dummy variable, so I can do this kind of manipulations, and the right hand side is all again the same. I'm not touching the right hand side. So now you see that so the e to the power ikx and e to the power ikx are actually similar. So you can actually match each of these coefficients, right, term by term. So each k element, k summand, you can actually relate term by term. So so let me write this in a more clearer way. Sum over k. So I have this j summation u I j psi j r k and e to the power I kx on the left hand side. Or let me also pull back this other thing as well. So I have this rotation operator acting on psi I k, and the rotation operator inverse multiplied by e to the power I kx, which is 0. Okay, so that means that because as you know that e to the power I kx, these are orthogonal functions, so that means that you can actually equate both of these sides with this e to the power I kx. So now, I mean, so the this last part is, so like this has to be 0 to satisfy this equation. Okay, so that means that I can take this thing, so if this is 0, then I'll have this thing. So you see that what I have done here is, I have started from the real space action of the rotation operators, then I have arrived at the momentum space action of this rotation operator. Okay, so then because my Hamiltonian is written in terms of these psi's, then I can easily find what is the, I mean, how does the Hamiltonian will change under this rotation. So and so let's call it equation 3, and similarly we will have the other equation for the psi dagger as well. Psi I k dagger, rotation inverse, and there is sum over j u I j psi j okay, so not the other way, psi j r k dagger and u dagger j I. Okay, so this is the action for the dagger, psi dagger. Okay, so these are the two equations that we will use now. So so as I mentioned before, if you have some symmetry, then that implies that in second quantized language, so it always commutes with your Hamiltonian. Okay, so but that might not be true when you write the Hamiltonian in the matrix form. Okay, so you will see that for anti-unitary symmetries, the matrix will not come out at always to be commuting. Okay, so it can be anti-commuting or also. So anti-commutation also might mean some symmetries. Okay, so this is something that that we know. If a Hamiltonian is invariant under a symmetry, then this has to hold. Okay, and the Hamiltonian is given by this block form summation over ijk psi I dagger k H matrix ij function of k and psi j k. Okay, so now so let's call this our equation 5. So I'll take equation 5 and I'll just act R and R inverse from the both hand side. Okay, so let's try to do this. So then we'll have R H R inverse. So that means on the right hand side of equation 5, so I'll have something like this: R psi I dagger k R okay, not R, so H I j function of k psi j function of k, and on the right also I have a R inverse. Okay, so now I'll just insert some identity operators here and there. So let's say here, so I'll just insert an identity. So this identity, for the identity I can write this thing as R inverse R. Okay, so because these are two operators, I mean inverse and the same operator, if you multiply, then it is just identity. So I have summation I j k, some rotation psi I dagger k, so the R inverse that I have inserted, and R, and then I have H I j function of k, and also I'll insert R inverse here, psi j k and R inverse. So now you know that, so I know this part and I know this part as well. So this is just our equation 3 and 4 that we have just derived, right? So I know how does the rotation operator act on these field operators in momentum space. So this is given by equation 3 and this is given by equation 4. So I'll just directly substitute those equation 3 and 4 here. So we will have I j k, and I'll have two new indices, so let's call them I1 and J1. Okay, and let's carefully write this. So the first term will be uj1, okay, not j1, u, what I'm doing, so psi, okay, so let me check this again. Yeah, so psi I dagger u I so okay, so u dagger then I and j. So this is a function of rotated k. Right, so j, so the indices are wrong, j and I, j1 and I, right? Yeah, so this is the equation 3, and then I have this R H I j function of k R inverse. Okay, and for the equation 4 we'll similarly write u j okay, so my power just went down, so let's see how long does the EPS gives me backup. So in case this goes off, then I'll join as soon as this will go on. All right. So let me open the curtains. Okay. Yeah. So I was writing this equation 4 here, so which would be given by uj, and so let me write this as I1 uj and j1, and then I have psi j1 rotated k. Okay, so all right, yeah. So now these are everything, right, that I need. And one thing that you will notice, that because this hij, so this is the ijth matrix element of the Hamiltonian matrix, so which is just a constant number, right? So what will happen is this rotation will actually go through, and it will end up with this R inverse, and I mean this R and R inverse will just vanish from this middle. So I can remove this R and R inverse. Okay, so this is I can do this because each ij, so a ijth element of the matrix is just a number, right? So that's why I can do this. All right. So now I can see that there is some structure which is emerging. So but I have to take care of this rotation. So what I will do is, so I will again, because k is the dummy variable, I will change k to be k, or let's say I will change rk to k. Okay, so something like that. So then what will happen is I will have so in the same equation I'll just copy and paste it. So in the same expression I have so this will be replaced by k. Okay, and this will also be replaced by k, but when I have just single k, it will be replaced by R inverse k. Okay, so okay, things are getting simpler. So now what I can do is I can actually do some summation over this internal indices. So let me just write it first. So this is u dagger h, which is a function of R inverse k, and then again u. Okay, and then the I1 the j1 oh, okay, so the I1 on j1 matrix element of this j1 k, and then I have a summation over I1 j1 and k, right? So now, so this is so now I have been simplifying only the right hand side, so but still I have the left hand side which I'll have to take care. So the right hand side, so this is just right hand side, and the left hand side is, it is given by this rotation h, rotation inverse, which is same as h, right? So this is same as h. So the right hand side is simply I1 j1 k and psi I1 dagger k h I1 j1 k and psi j1 k. Okay, so now you see that, so I have actually basically written both right hand side and left hand side in the same footing. Okay, so only this matrix element is actually different. After doing all of this song and dance, I see that this element is actually different, right? So but I can equate these elements, because the symmetry constraint that implies that each of these elements are actually same. So that means if I write matrix h of k, okay, then this will be related to u dagger h of R inverse k and u. Okay, so that means that so let's do one more simplification. So let's write this k to be rk. So then the left hand side becomes Hamiltonian of rotated k, and the right hand side becomes u dagger Hamiltonian of k and u, right? So you see that if you are Hamiltonian, the second quanta is Hamiltonian. So let me write all of this. If second quantized H was invariant under this rotation operator R, that would imply that this would commute with the Hamiltonian. But if you write it in matrix form, the exact same relation in matrix form turns out to be Hamiltonian matrix of a rotated k is given by u dagger h of k by u. Okay, so we see that this symmetry actually gives additional constraint, right? So this is a constraint, right? So if we do some rotation, then my rotated Hamiltonian would be similar to the Hamiltonian times this rotation matrix. Okay, so this is additional constraint that the symmetries give rise to. Okay, and so you can take any rotationally symmetric Hamiltonian, or you can, for example, you can take something with a less symmetry. For example, you can take a square lattice, right? So square lattice has a fourfold symmetry. Okay, so it doesn't have a continuous symmetry. So you will see that this this kind of fourfold rotational symmetry will give additional constraints to your Hamiltonian. So that means your Hamiltonian with this kind of symmetry cannot have any arbitrary form. It has to obey this constraint because of symmetry. So symmetry is a very sacred principle which the Hamiltonian has to obey. Okay, so now all of these things, rotation, these things are all unitary symmetries. Okay, so this for the symmetries, this u's you will need, these are all unitary. Okay, so now you can do the similar thing, and you can also do this for anti-unitary cases. Okay, for anti-unitary, so I'll not show you how to do that, but I'll show you what happens if we have anti-unitary symmetry. So if we have, let's say, some anti-unitary symmetry, so like I mentioned, three anti-unitary symmetries. One is time reversal symmetry, time reversal operator, which is given by ut times the conjugation. Okay, and the other is given by c uc times k and s. So let me write all of this. So this is called time reversal operator. So this is called charge conjugation or particle hole symmetry, particle hole operator. And this is called a chiral symmetry operator. Or chiral, okay, operator. And all of these things that I have written is so this is a unitary, and the k is a conjugation. So these are all in matrix form. So all of the symmetry operators I have written in the matrix form. So in second quantization, all of this implies the same thing. So in second quantization, so time reversal symmetry would imply that your Hamiltonian will commute with a second quantized time reversal operator. And similarly, charge conjugation symmetry would imply, so the Hamiltonian will be some cursive C, so H C inverse. So the Hamiltonian will be invariant under this operation. So chiral symmetry implies that your Hamiltonian will be invariant under the action of the second quantized uh, 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 symmetry operator. Okay, so this is nothing new. So this is, you already know, this already also holds for for unitary or anti-unitary symmetry. So the only difference comes when you convert this into this matrices. Okay, so for example, if you do the same exercise and convert this into matrix forms, so you will see that the constant given by these operators are like this. So T block Hamiltonian and T inverse is given by h of minus k. So that means that if your Hamiltonian has to obey the time reversal symmetry, then the Hamiltonian has to obey this, the Hamiltonian matrix has to obey this constraint. So the h of minus k is related to h of k with some rotation times the conjugation. Okay, so I'll show you so I'll elaborate what does this mean in a minute. So the other symmetries, they impose that, for example, the chiral symmetry impose that the Hamiltonian has to obey something like this. And you see, these are nothing like commutators. Okay, this can be very weird kind, this can be anti-commutator and all sort of things. Okay, so then S H, so this is the chiral symmetry operator. S inverse is given by h of minus k. Okay, so just to remind you, the chiral symmetry operator is nothing but the C times T, so charge conjugation times the time reversal operator. Okay, so let's take this time reversal symmetry and let's try to simplify and see what how to understand this expression. So what is the constraint on this Hamiltonian? So let's try to understand that. So if you have spinless Hamiltonian, let's say spinless fermion, so then these things are these things get simplified a lot. So then the time reversal operator is just the conjugation. Okay, so but if you have some spinful fermion, then this time reversal symmetry operator is slightly complicated. So it is given by I, sigma y, and conjugation. Okay, but let's first look at this simpler case when we have a spinless fermion, which is just the conjugation. Okay, so this equation, so let's write this as equation A, B, and C. So then equation A implies that conjugation and HK is equal to h of minus k. So here the arguments of the Hamiltonian are just the block momentum, and these are conjugation. Okay, so what does the conjugation do? It just conjugates any complex number. Okay, so it just makes hk to hk star, and then I'll have h of minus k. So that means that if my Hamiltonian matrix, so let's say you can write the graphene's Hamiltonian or some simpler Hamiltonian, you can check that whether this condition is met. Okay, so if this condition is met, then you can say that this is a time reversal symmetric Hamiltonian only for spinless case. Okay, so now, okay, so at the Hamiltonian level this is okay, but still this is not very clear. What does this mean? So let's look at the eigenvalue equations of this hk and h minus k. Okay, so the eigenvalue equations are given by h of k is equal to h of k acting on some some eigen function psi k will give you en k and psi of k, right? So, and similarly if you write h of minus k, so you will get a similar equation. and the operation of this time reversal operator on the wave function, it will just so let me write it as okay, so let me write it as T inverse is equal to, it will just make it to be psi of minus k, and you know what is the operation of this T on this psi, it will just conjugate it, right? So it will make it psi of k star is equal to psi of minus k. So this is the action of time reversal operator on this wave function, right? Or this eigenvectors. So these are two eigenvalue equations, 1 and 2. So what I will do is I will take equation 1, okay, and I will just conjugate it. So it becomes h of k star psi of k star en of k, and so for any Hermitian operator the eigenvalue is always real, so the conjugation of real is real, right? So I will just keep it as it is, and psi k star. Okay, so from time reversal symmetry we already know that this relation is true. H of k star is just h of minus k. Okay, so I'll write this as h of minus k, and you also know that the psi of k star is given as psi of minus k, right? So I'll write psi of minus k, en of minus k, and psi of minus k. So we see that okay, so en of k actually, yeah. So we see that we have started from this equation 1, okay, and we have just take a conjugation, and we have used this symmetry properties of the Hamilton and the action of this time reversal operators on this wave function, right? So then we see that we get back the eigenvalue equation for psi of h of minus k, but now the eigenvalue is replaced by en of k. So that means that, and the psi's are actually I mean so which actually means that so en of k is same as en of minus k. Okay, so we can try to imagine how does the eigenvalues look like. So for example, in the 1D, so if you have, this is your k axis, so if my eigenvalues are even function, so like this is an even function, imagine it is an even function, so this is an even function, so that means all of ek, for all of ek there is some minus there is some e of minus k. Okay, so if your energy eigenvalues are even function, at least for spinless case, then that implies that you have time reversal symmetry. Okay, so that is, I mean, that is the simplest way to understand the time reversal symmetry. You look at some bands and see that around this middle or around some reciprocal vector by 2, so you will see that if your band has this even symmetry, then it will always have to obey the time reversal symmetry. Okay, so now this is a simple case for a spinless fermion, but as soon as you incorporate spin, then this actually becomes a little bit cumbersome, but I mean this is still doable. So let me directly write the answer. If you have spinful Hamiltonian, or let's say spinful fermion, okay, and time reversal symmetry. So under this, so my Hamiltonian will have to obey sigma y is equal to h of minus k. Okay, so it is not just a simple conjugation, so it is on top of conjugation there is also multiplication sigma y. Okay, so this sigma y keeps track of the fact that because of change in the direction of time, you always change the sign of the spin. Okay, so that is taken accounted by this, that is given by this sigma y. Okay, so any questions? Okay, so you can actually do this similar analysis for the other anti-unitary symmetries as well, and you can try to find that how does the dispersion or the band look like for different symmetries. So for example, let's say if you have particle hole symmetry or charge conjugation symmetry, so if you do the similar exactly same analysis, or let's say for spinless fermion, if you do the analysis, so you will see that for particle hole symmetric it will have to have even number of bands, and for each of the En of k you will have a similar E of minus n minus k. Okay, so for example, so like in this band structure that I have drawn here, so this and this, so in opposite k and minus k, so if this is minus k, then this is k. So if you have this kind of band structure, so that implies you have particle hole symmetry. Okay, so then I mean particle symmetry means that if your eigenvalues match for match for k and minus k. Okay, so with a minus, with a minus, if it matches, then that means you have a particle hole symmetry. Okay, so the last, the antimateria symmetry that we are talking about is the chiral symmetry. So for chiral symmetry, the band structure look actually just symmetric, fully symmetric. So the condition for here will boil down to, for each of the bands we have minus E of n k. So for example, for each of this thing, you will have another partner sitting on the above branch. Okay, so these are depending on different symmetries how your band structure will look like, or this is the easiest way to find out what is the symmetry from the band structure. Okay, we have just to look at the band structure carefully. So these are all the non-unitary and anti-unitary symmetries that you can think about. Okay, so now it turns out to be there is no other symmetry that you can write. So any other symmetry you can write will be related to this by similarity transformations. Okay, so these are the three unique symmetry operations that you can write. Okay, so now we can actually classify all possible block Hamiltonian given these three anti-unitary symmetries. Okay, so you might think that, okay, so a block Hamiltonian can be of any dimension and you can put anything in this Hamiltonian matrix. Then the possible, I mean it cannot be possibly classified. It is like an infinite number of combination that you can make a Hamiltonian. Okay, but you will see that is not the case. So if you are talking about only anti-unitary symmetries, you will see that these three symmetries will restrict the number of Hamiltonians that you can write from infinity to a mere, some 10 number of Hamiltonian you can write. Okay, so what do I mean by all of this? So let me try to explain. So here, so we'll assume this kind of notation. So if some operator commutes, okay, so we'll write plus 1 or minus 1. Okay, or let me first write it. If an operator doesn't commute with Hamiltonian H, then for that operator we will write as 0. Okay, and if it commutes, then we will directly write as plus 1 or minus 1. So the time reversal operator, for example, t square is equal to 1, okay, for spinless fermion, and t square is equal to minus 1 for spin half fermion or half integer any fermions. Okay, so this plus and minus, plus 1 and minus 1 indicates the sign of this t square. Okay, so similarly for p square also we can have plus and minus 1 and the particle hole symmetry operator. So I was probably writing it as C, right? So So that means that I can actually make a chart of all of these numbers. So time reversal symmetry, charge conjugation, and S. So S is given by just T times C. So I'll write all of these possible signs that I can write. Okay, so that is actually counting how many Hamiltons that you can have depending on this symmetry. How many Hamiltons you can have. For example, the first combination I can write as, let's say I do not have time reversal symmetry, I do not have conjugation symmetry, and I do not have a chiral symmetry as well, because so if T is 0, C is 0, S is automatically 0, right? So so like this, so I mean, you can think of this like as a truth table. So I am writing all of these possible combinations, right, in the truth table. So then I can have a +1 for the charge conjugation symmetry. Okay, so let me just write down all of these things so that it will become clear. So I can have -1, 0, 0. So I can have +1 for the time reversal symmetry. Then I can have 0, +1, -1, 0, 0. Okay, not 0, +1, +1, -1, 0, +1, -1, -1, -1. Okay, so these are all possible symmetries that I can have. So 0 means I do not have that particular symmetry, or +1 and minus means that I do have that symmetry in the Hamiltonian, but the sign may be +1 or -1. Sign of T square operator or C square might be +1 or -1. So let me fill up the third column as well. So this will be 0, this will be 0, this will be 0, this will be +1, this will be -1, this will be 0, this will be -1, this will be +1. Okay, so you see that how many combinations I could write. So I could write total 9 combination. Okay, so that this number 9 is actually kind of clear because your time reversal operator can take only 3 values, T0, +1 and -1, and charge conjugation can take 3 values, 0, +1 and -1. So this 3 times 3 is 9. Okay, but so there is one case that we are missing. So it has been seen that even if T is 0 and C is 0, we can still have S is equal to 1. Okay, so that is some anomaly kind of thing that you have. I mean, that kind of Hamiltonian you can have. So on top of this 3 times 3, we will have to add that additional one case that we have left in this whole table, because this table is constructed for S which takes account of T times C, but this S is equal to 1 when T is 0 and C is 0, that doesn't clearly come from T, I mean just the multiplication, right? So then for this thing this is the total combination of the symmetries that you can have is 10. Okay, so this is actually this is in literature this is called 10-fold classification. So there are many modern algebraic way to show this in a more rigorous way, but this is just from a simple combinatorics that I showed you. Any block Hamiltonian that you can write, any possible block Hamiltonian, any dimension, okay, and whatever you can think about. I mean, you can go crazy. Okay, so that all of the possibility of such Hamiltonian is actually if a very small number. It is just 10. So in whole universe you will get only this 10 type of Hamiltonian. So that means that, so you can write obviously different kind of Hamiltonians, but I can do some kind of transformation to the Hamiltonian and I can match them. Okay, so from the perspective of symmetry, it is just only there are 10 types of Hamiltonian that you can have. Okay, and depending on which symmetries you have, so this has actually different names. Okay, so let me quickly show you what does this yeah, so let me quickly copy something. So now this is something called the okay, my screen got again stuck. Okay, so let me rejoin again, I guess. Alright. So now this thing is called a periodic table for topological insulators. Okay, so what does this mean? So this is a very important thing in condensed matter physics. So like I have written all of the possible combination of these three symmetry operators, right? So this T is time reversal, C is charge conjugation, and S is the chiral symmetry. Okay, so you see that so here all of the possible combinations are written. So plus means +1, minus means -1. Okay, so like I have just written these things, and you see that there are 10 combinations. Okay, and depending on what symmetry do you have, these are called different classes. Okay, so these are called Cartan classes, but I mean, which is not important for us, some nomenclature. So depending on some symmetry, for example, this in the first row, you see that time reversal symmetry is 0, C is 0, and S is 0. So that means you have no symmetries in your Hamiltonian at all. Okay, so if you do not have any symmetry, and then if you look at so if you look at, okay, what is the topological invariant, what is the value of topological invariant that I can calculate? So this is given by in the following section. Okay, so for the first row it says that, and so this top above thing is the dimension. So for example, the first row tells me that if I have none of the symmetry, then in the 0th dimension, so that means I have, if I just like a point, if I write a Hamilton for some points, some orbitals on that point, so then my topological invariance will be given by integers. So Z means the group of integers under addition. Okay, so the topological invariance will be given by, in 0 dimension, will be given by integers. Okay, so then you go on to dimension 1. So then you go on to dimension 1. Okay, and you see that it is written as 0. So that means if you have no symmetries, then in dimension 1 you have a trivial insulator. So trivial insulator means, so I have a, in the bulk I have a gap, and also in the edge I do not have any states, right? So that is like the normal insulator that we have learned about in the band theory. Okay, so 0 means normal insulator, but again in dimension 2 we see that it is a topological insulator, insulator. Okay, so because I have this Z are integers under the group of integers under addition. Okay, so for example, let's look at this A3 group, A3 class. So here I do not have any time reversal and chiral symmetry, but I have only this time reversal or particle symmetry, but I have only this chiral symmetry. Okay, so and it tells me that if I have this, if I am in the second row, then in 0 dimension I can only have a trivial insulator. Okay, I cannot have any topological things. So in the 1D I can have a topological insulator, and in 3D I can have a topological insulator. In 4D it is just a trivial insulator, and so on and so forth. Okay, so then on the other these three things, for example, if you have heard about SSH model, so SSH model is a topological insulator in 1 dimension. Okay, so you can calculate an integer topological invariant for that SSH chain. Okay, which we will try to do if we have some time today. So that SSH model belongs to the BDI class. Okay, so SSH, so which is the simplest topological invariant you can think about in 1 dimension. So which has time reversal symmetry, charge conjugation symmetry, and also the chiral symmetry. Okay, so then this periodic table tells me in dimension 0 I can have this Z2 invariant. Z2 invariant means I can have either 0 and 1. Okay, so Z2 means the modulo 2 group. So if you take all integers and you take a modulo with 2, so that will give you Z2. So Z2 means 0 and 1. Okay, under addition. So the Z2 means that I can have these two topological phases. So 0 will mean I have a trivial phase, and if the topological invariant is non-zero, that will mean that or 1, that will mean that I am in a topological phase. So on the other hand, in 1D, as I mentioned that SSH is a topological insulator, you see that this is given by a group of integers, right? So yeah, you can find out different elements will belong to different groups. For example, you can try to see that for example, graphene. So in graphene you do not so okay, so where the graphene will fall is, so in graphene you do have time reversal symmetry, okay, and you have charge conjugation, okay, and you, so the sublattice symmetry is 0. So you see that it is given by this 0. So graphene, just the intrinsic graphene doesn't have any doesn't have any topological invariance. I mean, this is not a topological insulator. Graphene is not a topological insulator. So on graphene, if you add additional complex hoppings, I mean, that means if you write the Haldane model on graphene, then you will get a topological insulator. Okay, so that is some specific model which has a non-trivial topological invariant. Okay, so this is called so for your reference, so this is called a topological periodic table of topological insulator. Okay, so if you have any Hamiltonian lying around, or if you are working on some Hamiltonian, you can take that Hamiltonian, you can do all of this time reversal, you can check whether it has time reversal symmetry, charge conjugation, or this chiral symmetry, and then, I mean, in which dimension you are writing the Hamiltonian, you can try to figure out just from this table, will there be a topological phase, or it is just a trivial thing, or trivial insulator. Okay, so now when you have figured it out, okay, whether it is topological, then the next task is to find out what is the topological invariant. Okay, so this table tells me, okay, there will be some topological invariant, but this doesn't give me directly a formula of that topological invariant. Okay, so this is the limitation of this periodic table. Okay, so then you have to go finding, okay, for this symmetry, how can I write a topological invariant, and then that becomes a complicated task. So let me write down some typical topological invariant that you will see in condensed matter here and there. So for example, let's say that we are in class A. So class A means, so this symmetries, I have none of the symmetry. Okay, and I am in dimension 2. Okay, so this already tells you that you are expecting a topological invariant which is integer, which can be any integer. So let's try to find out what is the let's try to see what is the formula for that topological invariant. Okay, so let's say your Hamilton, the eigenvalue equation is given by hk, then unk is given by enk unk. Okay, so the n is the band index, okay, and h is the Hamiltonian, obviously. So then, so you can define something called a Berry connection. So you can find some references, some simpler references of about Berry connection. So this Berry connection appears when you have some adiabatic deformation in the Hamiltonian. So if you want to read more about this, you can try to figure out. So there is some section in Griffith's quantum mechanics when they talk about Berry connection. So so Berry connection is something like, so it is like some generator of a adiabatic deformation. Okay, if you like. So the Berry connection, so it is written by A of mu, A index mu k, which is given by I un k. So here we are in 2D. Okay, so all of these k's are actually 2 vectors, so I am not being very careful in writing the vector signs, but yeah, so it's a derivative un k. So this del mu k is just your del kx or del ky and the mu component of this. So mu is just 1 or 2, right? So if you have defined this Berry connection, then from this Berry connection you can define another quantity which is called the Berry curvature. So Berry curvature is given by, so if you take this A and if you write this as a matrix, so the matrix element will be A1 K, A2 K and 0. Okay, and then if you take a cross product of this vector, so the thing that you will get is called a Berry connection. Okay, so the Berry connection will be given by, so you can easily calculate this cross product. So let me write it. So let me write it x hat, y hat and j hat, z hat. So del x, del y and del z, and we have a let's say ax of k, ay of k and 0. Okay, so let me write this as ax and ay2. Okay, so then you see that, so for the x hat, what we will have here is for the x hat, so this will go and hit 0. Okay, and the delta z will act on this, but this doesn't depend on this any of these z coordinates. Okay, so that is a trivial thing. And for the y also, you see that this will act on here, so this doesn't depend on any kz, or there is no kz in our case, and this will give us 0. So only the component which will remain is given by z hat, then del y acting on axk minus del x acting on ayk. Okay, so you see that this is actually very much, so the f is like very much similar to the magnetic field, and the Berry connection is very much similar to the vector potential. So as if that, so these are like a magnetic field in the block in the momentum space, right? So yeah, so you can think about this in the electrodynamics way if you like. So the f is just this. Okay, so now, so after introducing this Berry connection and Berry curvature, so now I'll introduce what is the topological invariant, right? So we already know there is a topological phase that I can get a topological invariant, but now this is for the first time I'm writing the topological invariant. So this is called the Chern number. So the Chern number is given by I by, so I have actually, so there is no, okay, it's fine. So I by 2 pi, and then I have this 2D Brillouin zone on which I'll do the integration times this f of k. Okay, so if you calculate this, when you have no symmetries at all, you will see that this will give you some integer. So these integers, they belong to this z group, right? So integer upon summation. So this is the topological invariant that you are looking for. So if you are in 2D and if you have no symmetries at all, so then this will always give rise to some integer, okay, which is guaranteed. Okay, and this Chern number on the related note is actually related to the this Hall effect or anomalous Hall effect. So if you calculate your conductivity is xy component, so you will see that this will be proportional to c times e square by h bar. Okay, so this is directly related to Hall conductivity kind of thing. Okay, so in Hall conductivity, this c will emerge. So like, so this is like, so this is also called anomalous Hall effect, because here we do not have any physical magnetic field, but somehow this f actually acts as some fictitious magnetic field in the momentum space. Okay, so that will give rise to the similar kind of effect, and we will have a Chern number. Okay, and this Chern number will tell me, and this Chern number is also related to the number of edge states. So today in the beginning, as I mentioned, that there is a something called bulk boundary correspondence. right? So that means if I know about information of bulk, so that means if I have a block Hamiltonian, or if I am in the block space, I can calculate the C, right, by doing the whole integration of the Brillouin zone. Then if I look at the boundary also, so I'll see that there will be, so if this is my sample, and I mean, this is my, let's say this is my sample, so I'll see that on the edge, so there will be C number of edge states which will be flowing on this system. Okay, so this is the bulk boundary correspondence. So if I know the Chern number, which is a bulk quantity, so to know it I have to write the Hamiltonian in the block space. So that means I'll need to have an infinite Hamiltonian or periodic Hamiltonian. So that would immediately imply that as soon as I make a finite edge in that system, that will tell me that will give me directly the access to the Chern numbers. Okay, so this is not a, I mean you cannot prove that, but I mean it has been seen that this is always there. Okay, so this is like, I mean it is a very sacred kind of principle that is always obeyed. Okay, so yeah, so this is a bulk boundary correspondence. Okay, so this is one of the topological invariant that you can think about. Okay, but so this is again this is true in if you are in dimension 2. Okay, so what happens if you are in odd dimensions? For example, what happens in dimension 1? So let's go back to periodic table and let's see what we can have in odd dimension. So so in odd dimension, so for example, so this is my let's say in the lowest dimension 1. Okay, so in the odd dimension, if I have chiral symmetry, so then it tells, this periodic table tells me that I will have some topological phase, some non-trivial topological phase. So I can have topological invariants which will give me integers, right? So from that, so let's try to figure out that if I have only the chiral symmetry, then what will be the form of the topological invariant that you can write down. Okay, so let's try to see what you can do here. So previously I told you that so if you have chiral symmetry, so then let's write the Hamilton as this S, or let's say it says gamma. So if you have chiral symmetry inverse, so then that will give you minus of h of k. Okay, so that is the action. I mean, if you have chiral symmetry, then the Hamiltonian's matrix is constrained by this equation. So I can actually write it in a different way. So gamma hk, and I can take the gamma inverse to the other hand side, so which becomes hk times gamma. Okay, so so if I bring everything to the left hand side, you see that you can recognize this is an anti-commutator. So that is, again we are coming back to the point that when we mean symmetry, it is not always we are looking for commutation, it also can be anti-commutation. For example, in this particular example, we see that some matrix, matrix, it anti-commutes with our Hamiltonian, but still there is a symmetry. So for so this gamma is actually these are actually unitary operator. Okay, so if you have this kind of symmetry, so then so this anti-commutes, right? So but we know that if something commutes, then we can write the Hamiltonian in the basis of that particular operator, and it will be immediately block diagonalized, right? So we know that, but that is for commuting Hamiltonians. Operator. So for commuting operator, I know that I will have simultaneous eigenstates, and if I write the Hamiltonian in the basis of that operator, then I will get a block diagonal form, and each of the blocks will be determined by the eigenvalues of that particular operator in whose basis I have written this Hamiltonian. Okay, but this is not true for anti-commuting. So what happens for anti-commuting operators is that, so if you write the Hamiltonian in the basis of anti-commuting operator, then it is not block diagonal, it is block off diagonalized. So that means that your Hamiltonian will be broken into two off diagonal blocks. Okay, this is a fact. I mean, you can believe me, this is a fact which is hard to prove, but I mean, you can check for smaller matrices. Okay, so I'll show you, I mean, one example probably. So let me just repeat this again. If you have some commutating operator, then in the basis of that operator, your Hamiltonian is a block diagonal. But when you have anti-commuting operator, then in the basis of that operator, you have a block off diagonal Hamiltonian. Okay, so it is fully off diagonal Hamiltonian. So when that will be the case, so let me write the, I mean, in symbols. So if your Hamiltonian has that, I mean, is written into the block diagonal Q of k and Q of k. So dimension of this Q of k can be anything. It can be 2d3, I mean 2 cross 2, 3 cross 3, n cross n, whatever. Okay. Then, so the topological invariant in 1D is given by, so it is called a winding number. Okay. So this is given by integration of the over the Brillouin zone I by 2 pi, and then you have trace Q inverse D of Q. Okay, so which is same as derivative, or let me write it as yeah, d dk, yeah, so derivative of log Q. Okay, so I mean, so this is a nice identity that you can probably note. So if you have a derivative, so let's say ddx acting on a log of some matrix. Okay, so then you will see that you will get, I mean, if you simplify this, you will get a trace of M inverse. This is actually a determinant. Yeah, so this is Q is determinant. So M inverse ddx of M. Okay, so this is a nice matrix identity which might come handy sometimes. So this is the topological invariant for 1D. Okay, so this is called a winding number. Right, so this has many, I mean, you will in literature, so you will find there are many forms of this winding number. Okay, so this is one of the form, this is not the unique form, but all of this will give you rise to the similar same integer, same topological invariant. Okay, so yeah, so this winding number, so in 1D, so this is related to something called Berry phase. So what is the Berry phase? So Berry phase is, so if you integrate over the connection, so Berry connection, okay, over the full Brillouin zone. Okay, so this is true for 1D. So then you will get a 2 pi, or so you will get some phase. Okay, so this is called the Berry phase. So it turns out that in 1D the Berry phase, I mean, this is also called the Zach phase. So this, the alternative form that I was talking about, is given by, so this, so integration over Brillouin zone. So there is I by 2 pi, and then there is uk. So uk is, remember, this is the eigenvector of, let's say, of any one of the state, and then derivative and unk. Okay, so if you calculate this, you will see that this will give you some integer which is some winding number. Okay, so there is another alternative form for 1D, so which is given by something like this: minus pi 2 pi d tilde k and d tilde k z component of it times dk. So what are the d tildes? So d tildes are given by d, by modulus of d. And what are these d's? So you remember that any 2 cross 2 Hamiltonian, okay, so this is actually true for okay, this is true for actually this one dimension. So let me write it properly. So 1D and 2 cross 2 Hamiltonian. So you remember that Hamiltonian you can always write as sigma dot some d. Okay, so you can write in terms of Pauli matrices this block Hamiltonian. So then you normalize this d vector, right? So this is the normalized d vector which we call the d tilde, and then you take a cross product of this kind of thing. So that will also give you the same topological invariant. Okay, so now so I have talked a lot about this topological invariant. So let me show you one of the topological invariant in action. So I will consider SSH model. So I have talked about SSH model in some previous videos, but just let me remind you quickly. So SSH model is a bipartite lattice. That means that each of the unit cell has two sublattice. Okay, so these are two different sublattice. So let's call this A and B, and so on and so forth. And so you know that from in tight binding approach, what we do is we write all possible hopping parameters between different sites, right? So there can be a possible hopping between these two different cells. Okay, so let's call it W, and there can be hopping in the same unit cell. So let's call it V. Okay, so this is a toy model for a polyacetylene chain. Okay, so this is this is the simplest thing that you can think about when you think about topological insulators. Okay, so you can write the Hamiltonian. Okay, so the Hamiltonian is given by some. So now I have two flavors of things in each of the unit cells, so I'll have to keep track of that also. So let me write it properly. So Ci dagger A, Ci B with V. So this first term, so this is the hopping in the same unit cell, right? So this is the hopping in the intra cell. So some particle is actually hopping from one side to another side, right? So and then there is summation over all such unit cells, right? And then I have another part W, so summation over all of the unit cell. Then I have the intercellular hopping. So I'll have Ci plus 1 A dagger Ci B, okay, plus all of the Hermitian conjugates. Okay, so if you go to momentum space, okay, if you just do all of the Fourier transformations, if you go to momentum space, you will see that the Hamiltonian will be written in this form. So sigma dot d, where this dx, so these are all functions of k. So now I am in the block momentum, so I'll write all of these things as a function of k. So dx is given by v plus w cos k. So dy k is given by w sin k, and dz k will be given by 0. Okay, so these are the three d vectors, right? So now, as I mentioned before, that if you know all of these d vectors, so you can take help of this formula, okay, and you can do this integration over this 1D below zone, okay, and that will give you what is the value of this winding number. Okay, So for at least 1D, there is a very simple way to do this. Okay. So what we can do is we can try to plot these vectors, so dx and dy. So what happens is that when we go in the when k goes from minus pi to pi, because this is in 1D, this is just a ring, right? The Brillouin zone is just a circle. So when you go from minus pi to pi, then because I am coming back to the same point, then this trajectory of d would also be something like a closed line. Okay, it has to be a closed line because this is a continuous function, and if my k is coming to the same point, then d has to come to the same point, right? So it will be some kind of a loop. If I traverse whole k, then this will I'll traverse in the parameter space of this d in some kind of a loop. Okay. So so let's try to find out what the trajectory exactly is. So the trajectory, you will see that is very simple. So let me write this down. So the first equation, this is the first equation. So I am bringing the v on the left hand side. The right hand side is w cosine of k, and in the second equation, so I'll just keep w sine of k. Okay, so now I can actually just square these both equations and do a summation. So then what I will get is dxk minus v square plus dyk square is equal to w square. Okay, so now you see that in this parameter space of dx and dy, so this is just a equation of a circle. Okay, so the center of that circle is at, so my x coordinate is like shifted by v, right, and the y coordinate is not shifted at all. So the center is at v comma 0, and the radius is w. Okay, so it means that, so let's say if this is my v comma 0, then around that point the trajectory of d will be a circle with radius w. So this radius is, let's say, w. Okay, so physically what this formula does is, so like this cross product of this weird looking or weird looking formula, what it does is it actually checks whether my circle encloses the origin or not. So let me draw two different cases to exemplify. So let's say if this is my v0 and my w is something like this. So this is w, and on the other hand side, let me draw something like this. So this is my v0 and the w is something like this. Okay, so you will see that if you again go back to the formula of this d cross derivative of d and integration over the full Brillouin zone, you will see that it actually counts whether this d vector that captures the origin or not. So for example, so in the first case, so if I am capturing the origin by this circle, so the origin is actually some sort of a singular point you can think about, and you can think of this as a Cauchy's contour theorem, right? So whenever my contour that includes a singularity, then only I will have a non-zero contour integral, right? But if it doesn't capture any singularity, then I will just get 0 in the contour integral. So in the same sense as Cauchy's contour theorem. So you see that in the first case, I am able to capture this origin. Okay, so then this is actually this is if you again go back to that other formula, then you will see that you will get a winding number to be 1. Okay, but on the other case, it doesn't encloses the origin in the second hand. So then you will see that this is just a 0. Okay, and so whenever it will directly go through the this origin, so that origin is actually so whenever it will cross the origin, so this is actually a gap closing point. So at that particular point, the two eigenvalues become same. Okay, so that is a gap closing point. And if you are going through this singularity, then obviously you don't get anything quantized. Okay, so at that point you don't, this is ill defined, the topology is ill defined. So to have a topological insulator, you have to have a gap. So that means you have to have an insulator first. So if you are in a metallic phase, then topology is ill defined. Okay, so like, yeah, so these two are two different topological phases. And to go from one to another, so like if I am just pulling this circle down, then I have to go through this singularity. And by doing this drastic kind of change in the Hamiltonian, I can go from one topological phase, let's say 0 to 1 or 1 to 0. Okay, so this is a story about SSH model. So now this is everything in the bulk, right? So in bulk we have this topological invariant. Okay, but as I mentioned before, bulk boundary correspondence always holds, right? So now what is the effect of these bulk states, of this bulk invariant onto the edge states, right? So now if you want to have a look at the edge states, so first of all, then you have to you cannot put a periodic boundary condition. You have to have an open boundary condition, right? So that means the SSH chain is not actually connected in a circle, so it has two open ends. So whenever you will have the winding number to be 1, you will have zero energy eigenvalues, zero energy eigenstates. Okay, and if you plot the eigenstates, you will see that those eigenstates will be localized at the edges, and they will exponentially decay into the bulk. On the other hand, if you are in a trivial phase in SSH model, then you do not have any zero energy eigenstates. Okay, so you will not get any zero energy eigenstates at all, and all of the states, none of the states will be localized. So all of the states will be kind of here and there, it will be extended throughout. So this is, I mean, the bulk boundary corresponds that I was talking about. If you have some bulk invariant, then that immediately tells you that you have some edge states as well. Okay, so similarly, so for the Chern number case, so if you have a Chern number, so if your Chern number was 0, Chern number is some integer, then if you look at the edge, then you expect this C number of edge states propagating through this thing, propagating through the edges, and in the bulk everything is insulating. Okay, so I hope this idea is more or less clear. Okay, and so lastly I'll just quickly show you another calculation of Berry connection, and we'll finish the session. So let's say you have a Hamiltonian, Dirac Hamiltonian. So Dirac Hamiltonian means that, so this is a kx sigma x plus ky sigma y. So this is a Dirac Hamiltonian. If you find the eigenvalues, you will see that it is a Dirac cone. Okay, so they will be linearly dispersing modes. Okay, so now so this is one of the bands. So so this is the lower band, so it has two bands, and this is the upper band, right? So if you, let's say if you take the if you want to calculate the Berry connection for the lower band, what you will do is you will first start with the eigenvector of that particular lower band. So let me call it as U1. I mean, this is 2 cross 2 Hamiltonian, you can do everything by hand, and it turns out this the eigenvector is given by 1 by square root 2 kx square plus ky square. Okay, and this is a 2 spinner, right? So because the Hamiltonian is 2 cross 2, so the first term is given by kx square plus ky square square root, and the second element is given by kx plus iky. Okay, so now you can calculate the Berry connection, the x component of Berry connection, which is just I u1 of k del k x u1 of k. So if you do all of this derivative and simplify things, so you will see that this is given by ky divided by 2 kx square plus ky square. Similarly, you can calculate the y component, so which is similarly u1 of k del ky u1 of k, and this will be minus of kx 2 kx square plus ky square. So you know both of these component of Berry connections, and then you can calculate the Berry curvature, right? So the Berry curvature of band 1, so all of these things have index 1 because these are coming from band 1. So Berry curvature of band 1 is given by del x ay minus del y ax. If you calculate all of these derivatives and simplify, you will see that this is just basically some 2 kx square plus ky square z hat. So now, when it is interesting, the structure you will see that is very interesting. So like this, so this is like magnetic field from of a monopole. Okay, so if you ever try to write a magnetic field of a monopole, you will see that magnetic field is just monopole will be given by 1 by r square. Okay, if you ever try to do that. So but here we see that, so this is like in the analogy to the electric field, this looks like exactly like a monopole, but this is in a momentum space, right? So like some fictitious magnetic fields monopole is there, and because of that particular monopole I have all these topological effects and all. Okay, so I mean it is helpful sometimes when you bring this analogy of electrodynamics to this Berry connection and Berry curvature. Okay, so you can try to integrate on this Berry curvature, but you will see that the Dirac system, okay, it actually in 2D you will see that it has so it doesn't have time reversal symmetry. It has charge conjugation symmetry, but it doesn't have time reversal symmetry. Okay, so then it is actually trivial insulator. So if you integrate over this whole Berry curvature, you will see that this is I mean this will give you just 0. Okay, because this is a topological the Chern number is 0 because this is a topologically trivial Hamiltonian. Okay, so yeah, so this is some aspects or some main key ideas of topological invariance. So you can obviously find out more if you want to read more on this. I mean there are vast literature on this. Okay, and this is very interesting topic that which is active research, which is being actively researched on. So yeah, so any questions? So if not, then we will finish today, and we will continue again next week. All right. So thank you and have a nice weekend. Okay, I'll see you next week.